Hello physics students. In this video, you're going to learn about the types of motion caused by the magnetic force. And in some sense, the magnetic force is like any other force that we studied, namely that it creates acceleration. But because of the peculiar nature of the magnetic force, namely that it depends on the velocity, the types of motion are limited. To make you or help you see that, what I want to do is compare it to the electrical force. Now, the electrical force has no velocity dependence. F equals Q times E. Direction, magnitude don't depend on velocity. So what's possible then is if there's an electric field this way and I project a proton like this, it can accelerate in the sense of speeding up. So that will be pulled and go faster, faster that way. If I project an electron, or sorry, a proton, opposite of an electric field, the force will be this way. So I shoot like this and it'll go this way and slow down, also an acceleration. Or if I project the proton perpendicular to an electric field, then I can create parabolic motion like projectile motion with a force in one direction, acceleration this way, constant velocity this way. And another example, if I project an electron around a proton, then what can happen is I can get circular motion. So speeding up, slowing down, turning in circular motion, turning in parabolic motion, all three kinds of acceleration, speeding up, slowing down, turning. But the magnetic force, the magnitude depends on the velocity and so does the direction. Furthermore, when we do our right-hand rule to figure out the direction of the magnetic force, velocity, magnetic force, the magnetic force is always perpendicular to the motion, to the velocity. And that means there's no component in the direction of the velocity or opposite the direction of velocity. The magnetic force never speeds up or slows down a freely projected charged particle. So what are the possibilities then for the motion? That's the topic for today. Motion of a charged particle in a magnetic field. Two cases we're going to look at. One is, suppose I project the particle with a velocity such that the velocity and magnetic field are 90 degrees apart. In other words, they're perpendicular. So what I have here is an example of a magnetic field pointing out of the board. And suppose I project a positive, like a proton, in this particular direction. If I do the right-hand rule on that, what I would do is I would put my velocity down, like my finger like this, to indicate the direction of velocity. Then I'd have to swivel my wrist so that these three fingers point out of the board. So I guess I would do this like this, and I would see my thumb points towards the center of that circle. 90 degrees, it's not going to cause this to accelerate, speeding up or slowing down, but it will cause it to accelerate, turning. So this velocity, a little bit later, will turn toward the center of the circle. Maybe it's going down like this. If I repeat the right-hand rule here, velocity, magnetic field, thumb points again inward, like this. So that'll cause more turning. Right-hand rule again, force inward. So this force continuously turns with the velocity, always pointing to the center of that circle, and it creates circular motion. Another possibility is with the electron. I do the right-hand rule, same thing. I go velocity, magnetic field out of the board, and I see my thumb points away from the center of the circle, but because it's an electron, the force is the opposite of my thumb, again towards the center of the circle. So the proton will go clockwise, circular motion. This will go counterclockwise, circular motion. Okay, but nevertheless, the motion is circular. The magnetic force is the centripetal force. I'll talk more about that later. That means the work is zero for all instances because work is FD cos theta. And with a 90 degree between the force and the motion, you always get zero work, which means the kinetic energy stays constant, means the particle does not speed up or slow down. So that's another way, instead of thinking about Newton's laws, but also with energy conservation, to convince ourselves this doesn't speed up or slow down. Case two, the velocity and the magnetic field are not perpendicular. They're somewhere between 0 and 90 degrees. What happens is it forms, the particle traces out what's called a helix, like a spiral in a sense. Why is that the case? Well, I have a simple diagram here. I'll bring this closer to the camera. And so suppose I have a magnetic field like this blue arrow and the velocity like this. So notice they're not 90 degrees and they're not zero, somewhere in between. We could think of this velocity as having two components, one that's parallel to the magnetic field and one that's perpendicular to the magnetic field. If you do QVB sine theta with this component, that creates circular motion as we just discussed. Whereas QVB sine theta with this velocity component creates zero force because this velocity component and this magnetic field are 0 degrees with respect to each other. QVB sine 0 gives us 0. So this portion of the velocity creates no force. This portion creates circular motion because it's perpendicular to the magnetic field. So I am moving forward while also going in a circular path, moving forward with this component. And let me just show you that. So here is circular motion. Imagine the tip of the marker. I'm tracing that out, circular motion. Now let me move forward while I'm going in a circular path. What am I doing? I'm tracing out a helix as I've shown here. V perpendicular called circular motion, V parallel stays constant. So I should also point out that there is a third case where V and B are either 0 degrees or 180 apart, and then that's linear motion. No turning, no speeding up, no slowing down, zero acceleration because the force is 0. All right, let me create a pause to allow you to copy this down. All right, so now what we're going to do, this is a conceptual consideration about magnetic field, always called circular motion, never speeding up or slowing things down. Now, what are the kinds of empirical or numerical analysis that we might have to do? Here are some things. First of all, we got these charged particles, maybe protons, electrons, or I should even say these could be atoms that are ionized. So this could be like a chlorine atom, and this like a sodium atom, or ion, I should say. One's positive, one negative. So first thing I got to do, if I want to make a magnetic force, I got to get this thing moving in the first place. And I can't grab an electron and throw it, right? It's too small. So what I can do is use like a capacitor that's been modified and 2 plates, and then I drill a hole over here, and then the charged particles will experience a force because of the electric field in the capacitor, and they'll accelerate. And they'll shoot out this hole over here with some velocity, and then I could do my magnetic field experiment with that now moving charged particle. What you might have to do is figure out the speed of launch from, and the easiest way, you could use Newton's laws, but it's easier just to use energy conservation, that we've got electrical energy over here that eventually becomes kinetic energy. So by energy conservation, we start here. 1/2 mv squared is kinetic energy. Voltage times charge is the electrical potential energy for a given voltage, which is here of the battery. Solving for speed, I get this expression. Radical 2, the charge of the particle, voltage divided by the mass of the particle. So that's one thing that you might have to do with magnetism and motion, is first use electrical effects to figure out the speed. So the next thing, that then once this shoots out of this hole, we could put it in a magnetic field. I didn't draw the path because I already drew them here, so no sense being redundant. But before I move on, I want to just emphasize something I emphasized in the mechanics course. A lot of times when we have two things like this equal, we're saying that there are two forces that are equal. That's not what this equation is saying. If there were two forces that were equal, there would be no acceleration, which would mean constant velocity, linear motion. What this equation is actually saying is that to go in a circle, we require a centripetal force. It could be anything. It could be string tension, could be gravity, could be magnetic force, electrical force. So what is, in general, the force that we have specifically here? We have a magnetic force, only one force, the magnetic force. It's not balanced by anything. And this one and only force on the particle happens to be a centripetal force causing circular motion. That's really what this equation is saying in words. One force, and it makes it is a centripetal force creating circular motion. Let me create a pause to allow you to copy this down. Let's move on. Let's fill in the pieces of this, and what we're going to do is see what happens. So on the left side, mv squared over r, that's the centripetal force. Magnetic force, as we learned a couple videos ago, on a free particle is qvb sine theta. This is 90 degrees. In our experiment, we're not doing helix. We typically don't really, this is not really part of the AP curriculum other than as a concept. But here, we're going to project them 90 degrees to each other so that we make circular motion. And here's an expression that I boxed in. I'm calling that equation 2. And I didn't solve for anything because you might have to solve for any one of these variables. Maybe they want you to solve for the speed of something if it's going a certain radius in a certain magnetic field charge mass, like an electron maybe. So you put in here in a magnetic field, and we know the radius that we want it to go in. Well, what's its speed? Or maybe we know the speed, and we want to know the radius of the circular orbit, so we solve for r. Okay, so all different possibilities. Or maybe even we solve for q. We measure the velocity, the radius, and we want to know, well, what charge is this ion going around in a circular path? So, but the point is, you get to that point like that and then solve for what the problem is asking for. Another possibility is that maybe you have to solve for the period of orbit. In other words, the time it takes to go around once when this goes in circular orbit, that time, okay? So in order to do that, what we do is we take this velocity term, which I kind of color coordinated here, and we replace it in equation 1 with distance over time. Well, what's the distance? A circumference, 2 pi r, right? And then the time, we use capital T. That's came up in mechanics. Whenever something repeats over and over again, we tend to use the symbol capital T for the period as a special kind of time. And then we solve for the period. There it is, another equation. Now I just want to mention some patterns. From equation 2, we could see that the faster you project the particle into the magnetic field, if it goes slow, it traces out a small circular path. Project it even faster, it's going to trace out a larger radius path of a circular path. That's from this equation. We could see that V bigger, R bigger, if we have the constant mass, constant charge, constant magnetic field. So they're proportional to each other. Twice the speed, twice the radius of orbit. This equation is interesting because notice these are all constants. The mass of the particle, the charge of the particle, and the magnetic field we're shooting it into. And what that equation says is if I shoot something very slowly into a magnetic field, it goes around in a circle in a certain amount of time. I'll pick up a number, 2 seconds. And then I shoot it really fast. People say, oh, that's going to take less time because it's going so fast. No, it has a larger radius. So it goes fast around a larger distance, still 2 seconds to go around. Slow, 2 seconds. Fast, 2 seconds. The period's independent of the speed. So a couple little points there. All right, let me create a pause to allow you to copy that last bit down. All right, one final part of the notes, something that's historic. So people knew that we had these electrons flying around in circuits and whatnot, and that there was even an electron that existed, but it's so tiny, no one really could figure out the mass and the charge of an electron, but people wanted to know. So they did an experiment, and they were able to figure out, we're going to see the charge over mass ratio of the electron. So let's suppose we start with, okay, let's see. So let's start with this equation right here, okay? So no, let's start with equation 2. Oops. Okay, so, and then the other thing that I want to do is eliminate the speed using equation 1. I erased it, but let's do this. We launched this electron using a voltage. So we would say like this. Because, you know, what good does it do us to have velocity when when we're shooting electrons, we can't even see them, but we know the voltage that we crank up the power supply to launch the electrons with. So now we're in good shape. We can measure this. We can also determine the magnetic field. There were, through different equations, you're able to do that. And so let's solve for this ratio of Q over M. The way I'll do that is I'll square both sides. And notice that what happens is we got this Q over here, and this squared. We could eliminate those. We also have this squared, and this mass. Okay? And so let's divide both sides by this M left over. So we'll have Q over M on this side. But I'll move it to the left. And what's left on the other side is 2V oops, I forgot the R squared here. There, okay. So here's what they were able to do historically. They were able to measure the voltage that they accelerated the electrons to, watch them and measure the radius of the orbit with a ruler, and calculate the magnetic field for a given situation. And they were able to figure out what the charge to mass ratio is for an electron. They couldn't go farther. They could not determine the mass, they could not determine the charge, but they knew the ratio of the two, that number. Then, later, there was a scientist by the name of Millikan and he determined the charge of an electron as 1.6 times 10 to the minus 19th, which we know, we've used that before in this course. Once Millikan figured out the charge on an electron, he was able then, or humanity was able to plug this in here, and only M was unknown. And that's how they got the mass of an electron, which then they were able to solve as 9.11 times 10 to the minus 31 kilograms. So absolutely amazing result, able to determine the mass of an electron. You can't even see it, you can't even touch it, but you accelerate it, you put it into circular motion, and from voltage, radius, and magnetic field, you can then plug in the charge and get the mass of an electron. Really, really amazing moment for humanity. But let me create a pause to allow you to copy this last bit down. Okay, so that's those are the types of motion possible for a magnetic field. It cannot speed up or slow down a particle that's been freely projected. It can only turn it. And that means that either a circular motion with a constant speed or a helix with a constant speed, or possibly straight line constant velocity, are the only things the magnetic field can do for a free particle that's been projected in a magnetic field. So look back at equation 1, equation 2, and equation 3. The main idea of equation 1 is that kinetic energy equals electrical energy. Circle that in your notes. Or maybe the line below, 1/2 mv squared equals qv. That makes sure you know because that's what's going to be repeating in our analysis. The other main idea is the circular motion part, that Fc equals F magnetic, or remember mv squared over r equals qvb sine theta. Those are the main ideas that you want to have fresh in your mind. All right, so I hope you enjoyed the video. I'll see you in the next physics video.